Okay, hopefully everything was fixed. Um, I lowered the quality settings on the video, so hopefully there aren't as many drop frames this time. Although, given how things have been, that might be a total impossibility to remove them. Okay, so I'm trying to fix some settings. Okay, so hopefully, hopefully everything is all set. So this will be a live stream just like the other two that I've done on regular languages and context-free languages. Today we're going to be doing everything related to Turing machines and decidability. And then probably a week, I'm still deciding about this, uh, whether or not to do things on undecidability next week. If it's not next week, it's the week after. But we're definitely doing this one today. Hopefully no drop frames. Let me know if there are any problems with the stream in the chat and I'll try to fix them. Yeah, so the way the live stream will work, just like the other two, will be we're just going to cover everything in this entire section, and I'll take periodic breaks throughout. And if you have any problems that you want to see worked out, just put them into the chat. I have it right in front of me. So hopefully that's good. Anything else that I want to say? Yeah, so I'm not going to be covering like external test questions or anything unless you bring them up in the chat. I'm just going to do the standard material that's taught in the class and standard problems that are taught in the class, and it's just going to be a condensed version of if you took this, if you took the actual class. All right, so hopefully people are going into the live stream. Let me see. I'm just going to look at some analytics, see who's coming in. All right, so I would highly encourage you to please support the channel by liking, subscribing to the channel. It really helps us out. If you want to contribute in additional ways, there are other ways to do that in the video description. I'm doing one-on-one tutoring, private tutoring now. So if you want to schedule some tutoring, you can email me at my email in the description below. I have my email down there. So if you want to set something up over Zoom or something, then we can definitely do that. Yeah. So if you want to get some, if you just want some problems worked out or you're getting stuck on something, we have a Discord server as well as a Facebook group and many other things, many different avenues depending on what you like using. All right. Yeah, but yeah, everything that we're doing today is purely on Turing machines and decidability, and we'll start right on the hour. Yeah, it looks like I'm not getting any drop frames, so that's fantastic. So I'll have to remember to keep these settings for any future live streams. And new videos on Turing machines and decidability stuff start tomorrow. So basically you're going to be getting a preview of what we're covering tomorrow when this live stream comes out. If you're watching in the future, this is obviously irrelevant, but for those who are watching, Turing machine content videos are coming tomorrow. Okay. Got a lot of waters next to me because I'm going to be talking for a few hours. Yeah, so if you have any problems or any questions or anything you want clarification on, just hit me up in the chat and I'm watching it and I'm happy to help with any questions that you have. All right, so we'll start in a few minutes. So are there any questions that any of you have? I tried to decrease the latency for when the chat happens. from when I say something and when I see something in the chat. So hopefully it's a more interactive now, but I didn't make it ultra low latency, just low latency. Okay. Are there any questions before we start the stream? Yeah, apologies for anyone who was in the first stream and it just went kaput because I was getting so many drop frames that I needed to start a new one. And for some reason, you can't change the quality of the stream as the stream's happening, so you have to stop it. And for some reason, I couldn't start it back up again, so I had to make a new one. Sorry about that. I deleted the old video, so that was only like 2 minutes or something. So hopefully everything's all set. And it looks like it is. Okay. Any last questions from any of you? Yeah, so as always, if you want to support the channel, you can like and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support this channel further. And as always, thank you all for your support throughout these many months. I know it's been a very tough year, so I'm glad for all the support that you all have for this channel. Rahul says no. I'm not sure what that is referring to. All right. Oh, maybe like are there any additional questions that, okay, that's fine. Okay. So let's get it situated. All right, so welcome to the Turing Machines Decidability live stream. So we're going to cover everything about this that's taught in a standard class as quickly, well, not, I guess, as succinctly as possible and cover everything that is needed. So we did regular languages before, context-free languages now, a week ago. So now we're on this subject. So what have we talked about so far? So we have talked about these things called regular languages. And we've learned a bunch of regular languages, such as Sigma star is one of them, or empty set, or a bunch of things in here. And then we learned that there are, in fact, some languages that are not regular. So like 0 to the n, 1 to the n is not regular. And those fit within a bubble that we call the context-free languages. And we learned that there are a bunch of languages that are context-free but not regular. So like an example would be balanced parentheses. And there are many other examples that we can put here. But we also learned that, and actually another example is 0 to the n, 1 to the n, 2 to the n, where n is at least 0, and then the whole thing complemented. So not the original language, the complement of it. But then we learned that there are some languages that are not context-free. So like 0 to the n, 1 to the n, 2 to the n, where n is at least 0. Oh, yeah. The original language, not the complemented one. That one is not context-free. But if you think about it, if we are presented with an input on our computers, could we write a program to check whether it's zeros, then ones, then twos, and the same number of each of the sections? And yeah, that's pretty easy to do. We can write a simple Python script to do that. So what the question is, can we find a true, quote unquote, model for, and here's another quote, modern computers? Okay, so is there is there a model for the computers that we use every day? And because if there is, then recognizing this problem is really easy. And of course, any of these are really easy for a computer to do, but like these ones are also easy. So is there a model for the computers that we actually use? So the answer to this question is actually quite long, but the short answer to it is yes. And the corollary of that is that if some language, let's call it L, is not possible in this model, so if it's like equivalently not regular for a DFA, like it was impossible for a DFA to have a non-regular language. If there's a language that's not possible for this model, for the things that modern computers recognize, then of course, because it's equivalent to modern computers, we can't have a computer solve the problem. So we can't solve it on whatever the meaning of modern computers is. Okay, so so that's actually kind of important, and we're going to actually establish this fact later. But the model itself, and I'm going to skip all of the motivation behind it, is something called a Turing machine. Turing machine. So what is this thing? So this is a state transition model. So it's very, very analogous to like a DFA or a PDA. An additional fact that won't actually be relevant, but it's just easier to think about, is that it's a deterministic model. If I can spell deterministic, that'd be good. So it's no matter what state and thing you're looking at you are provided, the machine will do the same thing every single time. But the way that it's going to work here is that it will use something called a tape used. So how does this work? So the tape is a one-way, at least in the standard model it is, one-way infinite, although it's convenient to not have to think of it that way, but I'll just write it that way because that's formally what it is. So this is one-way infinite. Going to the right. So there's a left-hand end over here. And what happens is the input is presented on the tape. So I'll just stop there. So the input is going to be presented on this tape, and where each of the characters occupies one cell like this. Okay, so unlike, say, a PDA where we had a stack and we can only inspect the things on top of the stack, we're going to be able to look at anything on the tape that we want. Okay, so what we have at some random point is something called a tape head. So a tape head is basically like a pointer that looks at a cell, and then we can examine the contents on the inside of that cell. Indira, you may want to watch the CFL live stream then. So because this live stream is not about CFLs. Okay, so the tape head is looking at some cell like this one. So it's looking at the P right here. And the behavior of this tape head, so like what it can do, is that it can change the observed cell contents. It can do that if it wants to. So it can change it to some other value, possibly. Or maybe it could keep the same one. as well as move left one cell or right one cell. And so in order to actually carry out a transition in the machine, because it is a state transition-based model, so for a transition, what we do is we go from a state Q, let's say, to a state Q prime, and we also do these two things. Okay, so the transitions in this thing are going to change state just like usual, and the other behavior is that the cell contents could change to potentially anything, and the tape head moves right or left one position. And that's it. The only other thing is, so suppose that instead of the tape head being here, let's suppose instead that it was right here. So if the tape head's right there, and suppose that our transition said, okay, we're going to change the contents of this thing to whatever, it doesn't really matter. Now the tape head is going to move right one position. So if the input stops in this cell where the T is, well, what is the tape head reading in this position right here? Because the input is always a finite length thing. So what is the thing over here that it's looking at? So whenever we move right into new territory, we're going to allocate a new cell. So that's what, it's not really one-way infinite, it's one-way unbounded. So it's always finite in length, but we can always add more if we want to. So what happens is when we allocate a new cell, we're going to acquire something that we call a blank symbol. So this thing right here is a blank symbol. Okay, and whenever we allocate a new cell like that, we're going to keep it forever. Okay, so we're never ever going to delete any contents of any cell. Sorry, we're never going to delete a cell. So once we allocate a cell, we will keep it forever, and it's not going to actually change anything that we really care about. We may want to, for efficiency reasons, delete cells, but we're not going to focus on efficiency, at least in this or the next live stream. Okay, so what are we going to do here? How do we actually define this formally? So let's define it formally. So formal definition. It's funny, I write formal and then I do a shorthand of the word definition. So is the tape one-way infinite or two-way? So they're actually equivalent to each other. So you can either have it be one-way or two-way. In terms of being able to accept a given language, it doesn't matter which one you pick. The one that we're going to use is one-way infinite because it's just easier to think about. Because it's like, where do you actually start on the two-way infinite one? But if you have a way of doing it, then that's totally okay. I'm going to do one-way infinite. And as I said, it doesn't matter because you can have one simulate the other machine. So it doesn't actually matter which one you pick. Okay, so the formal definition is we have Q being a finite set of states, just like before. No difference compared to the other models. We have sigma being input alphabet, just like before, also finite. But because of that blank cell, and we may want to put something else on the tape, we're going to have something similar to what we did with the stack for PDAs, where we are going to have a stack alphabet. Not a stack alphabet this time, but a tape alphabet. And I'm going to call it sigma, just like before. I mean, you can call it whatever you want, but I'm going to call it sigma. Gamma. Gotta get my Greek letters straight. Okay, we have a Q0 being in Q. That's the start state, so nothing new there. how to stop the transition while going left if there's no blank at the left most of the string. Yeah, so that's one quirk of this machine, which is if you're at this cell and you want to move left, then you can either stop the machine because, and that totally makes sense because it's like you're trying to do illegal behavior, or you can just say, if I try to move left in this cell, I'm going to stay in this cell and then potentially change the contents. It turns out that either way, it won't change anything, but the way that we're going to focus on it is if you try to go left, while in here, the machine will stop. And either way is totally okay. Yeah, so that's the way that we're going to handle it here. But there's one quirk of this. Suppose that we don't actually, so the term for this is called hanging yourself, and it's not the best term in the world, but that's just the term that's used. If you don't hang yourself off the left-hand end of the tape, then then it could conceivably be that this machine just runs forever. So maybe we go back and forth between these two cells forever. And of course, we could try to check for this, but I don't want to actually have to think about that. And because we're changing the input possibly as we're going through, it's not like we're just going through the input and we're going to not change things. We could change things in the cells. So what we want to do is, since there's no way to figure out like when we're done reading the input, whereas with like a DFA, you can immediately tell when you're done reading the input, we need a special way of forcing the machine to stop. Because it's deterministic, you will always have a transition to apply no matter what. Because there's no popping of things on a stack or something. You're always looking at a cell on the tape. You're looking at something. So we're going to have the transition function be deterministic. So you will always have a transition to apply. Other than if you're on the left-hand end and you try to move. Setting that aside, you will always have a transition to apply. So that means it could conceivably be that the machine runs forever unless we force the machine to stop. So the way that we're going to do this in the formal definition is we're going to have two special states that are going to force us to accept or force us to not accept. So we're going to have two special states, one of them being Q accept, and we're going to, of course, call that the accept state. And if we enter that state, we are going to immediately accept at that point. And then Q reject is going to be, of course, the reject state. Okay. One thing that we can notice here is that Q accept is not the same state as Q reject for pretty obvious reasons. So that means that there are always at least two states in any Turing machine, at least in this model. There are two states. And one other thing about these two alphabets is we must have that the input alphabet is a subset of the tape alphabet because the input is presented on the tape itself. And for that reason, all of the input characters better be able to be put on the tape at some point. This is not the same thing as PDAs where the stack could technically have anything because it's separate from the input. Here, another thing that we're going to have is that the blank symbol, that special symbol, is in the tape alphabet, but it's not in the input alphabet. And the reason for this is, if we want this thing to be deterministic and we see a whole bunch of blank cells on the tape, if we allowed the blank cell in the input set, could it be that if we just see entirely blanks, does that mean that we empty string as input or several blank characters as the input string? We don't know for sure. And so we can't actually understand what the machine will do because the input is not precisely given. And also, the input is going to be left adjusted on the tape. At the very beginning, at least, it's left adjusted. Okay, so we also then need to define the transition function. I'm going to use a different color for that. So this is the transition function. transition function. So this is going to be, the things that we need to know are what state we're in. So that's going to be Q again. Times, well, we're going to be looking at a cell on the tape. So a tape character. Oops. So tape character. And we're going to, at the result of that, we're going to go to a state. We're going to write a cell on the tape in that cell that we're looking at. And we either move left or right depending on what the transition said to do. So the way that we're going to handle that is we're going to pick from the set L and R to mean L means we move left, R means we move right. And those are the only two possible behaviors of what the tape head will do. So to write this in English, so this is the before state on the left, where we were before. This is what is in that tape cell. This thing is the after state, where we go to after we apply the transition. This thing is what is written. Oops. What is written in the tape cell. And this, of course, is the direction of the tape head. Okay. So that's the transition function. And moreover, we also require that this thing be a total function. And remember from DFA land, total function just means no matter what before state you have and what thing is in the tape cell, no matter what pair that is, you always have a transition to do, always. And so that just means that the machine's deterministic. So it's just like a DFA, except we have more things in it. Okay, so let's do an example. And this example is in the Sipser book. So here we have a bunch of states. So here's Q0. In fact, there are going to be technically 7 states, but I'm going to write 6 states, and you'll see why in a sec. So we're going to have Q3 here, Q4 here, and one of those 2 states except. I'm not going to make the reject state, and you'll see why in a sec. So the way that the transitions in this thing are going to go is that we're going to have something that looks like 0, arrow, blank, and right. So I'll just write this here. So how do you interpret what this transition does? This is the observed cell value. The second thing, which is at the end of the arrow, is what is written value. And the R and or L, it depends, it tells us where to go on the tape, either left or right. Sometimes we will have a transition that looks like this, where instead of 3 things, we're going to have 2 things. So this transition says, if we see an X on the tape, then we're going to write an X onto the tape. Okay. The R here, of course, means move right. So this cell just means if you see an X, just skip over it, essentially. Technically, it always writes something to the tape, but in this case, it just writes the exact same thing it saw. Okay, so we're going to have more transitions that look like this. Another X goes to right transition. Let's see if I can. I'm trying to fit all of these on the same screen. It's going to be difficult. So we're going to have one coming down here, which is going to be 0 goes to right. This one coming back up is going to be changing the 0 to an X and also moving right. So far, every single transition is moving right, except now we're going to start doing the ones that move left. So this one is going to be not 0. It's going to be blank moves left. The Q4 state is going to self-loop on 2 sets of transitions, which are going to be just skip over zeros and skip over X's. Q4 is going to come back up here. When it sees a blank, it moves right. And the only other one is going to be one going to Q accept from Q1, and that's going to be blank moves right. Okay. And so those are all the transitions. Well, the thing is, this machine is not actually a Turing machine. And why is that? Think about, like, say, Q0. There's no transition coming out of here on the blank symbol. The only one that's presented is the 0, 1. So the way that we get around this, and the reason why I didn't make the Q reject state, is that all unwritten transitions go to Q reject. So no matter, so that it just makes the picture nicer. So I don't have to write every single possible transition. If you wanted to make the machine more formal, then obviously add all of the other transitions. But here I'm not caring about it being the transitions being absent, because they'll just go to Q reject. So let's actually try to compute a certain string on this machine. Okay, so what I'm going to do is I'm going to, let's try the input being 0, 0. Okay, so 2 zeros. And so the input alphabet of this thing, by the way, is just only zeros. So the input 2 zeros is part of the input alphabet. Okay, so let's actually try to simulate this thing. So the things that we need to note are, what are the tape contents at each point, as well as what state we're in, and where the tape head is on the tape. And the way that we're going to do that is, I'm going to write the 0, 0 like this, and we're going to change it in a bit. And I'm going to put under the cell where it's looking at what state we're in. So I'm going to, in this case, I'm going to put Q0 underneath the cell that I'm looking at. So the tape head starts at the first cell on the tape in the start state. So this case, I have Q0 looking at this cell because it's right under it. So it sees a 0 right here. So what the transition says to do, because there's obviously only one of them, is we're going to change this 0, only that 0, to a blank symbol. So the transition is going to be applied, and we are going to have the first 0 change to a blank symbol, because that's what the transition said to do. This second 0 was not touched, but the transition said to move the tape head right 1 position. So instead of being in that first cell, I'm going to now be looking at the second cell, which is what this 0 is. But I'm going to be in the state Q1. So it's a lot of things to keep track of, but once you start doing it more and more, you'll get the hang of it. So the things we keep in track of, what state we're in, which is the Q0 right here, what cell we're looking at, which is the one that's under, and what is the thing we're looking at. And we just see, okay, that's the transition we need to do. Change that 0 to a blank, which is what we did. We moved right 1 position, which is what we did. And we went to Q1 now, which is exactly what we did. Okay, so then now we will apply another transition, because we're not in the reject or the accept state. So it says, in Q1, what do you do on 0? Well, there's one transition that looks like that, changing the 0 to an X and moving right. So, so what we do is, the blank at the beginning was untouched. That doesn't change. This 0 it was looking at changes to an X, because the transition said to do that. And now it's said to move right, but there's nothing over here. So remember, we can always allocate a new cell, a new blank symbol at that point. So I'm going to allocate a new blank symbol right there. And so whatever state I'm in, I'm going to be looking at this third cell instead of the second one, because we moved right. And so then what happens is, we're going to be in Q2 now. So that's the state we're in. Q2. Okay, so what are we going to do here? Well, what does Q2 do on the blank symbol? Well, there's only one transition that does that, which is moving left. So it moves left and goes to Q4. So I'm going to be in this, looking at this X right here, because it moved left, and at Q4. note that this cell does not change according to this transition here. So we're going to have the following contents. So the contents of the tape did not change, but now we're going to be one cell earlier in the input and in state Q4. So Q4 here. Then what are we going to do? We're going to be in Q4. What does Q4 do looking at an X? Well, it just says skip over it and go left. So here we're going to have the exact same tape contents because it just said skip over it. And stay in the state Q4 because it was a self loop here. Now what does Q4 do on the blank symbol? It just says moves right and goes over to Q1. So the next set of the next transition is going to have it move right and not change the contents of the tape. And it's going to be in Q1 at the next, because it moved right, and now it's in Q1. Okay, so now what does Q1 do on X? Well, Q1 on X does a self loop, and it just skips over it. So the next part of the computing is going to skip over that X and still be in Q1. So it's going to be at the third cell now. Now what does Q1 do on the blank symbol? It comes over to the accept state. But now note that it does move right when it sees the blank symbol. So we do have to allocate a new blank symbol. So oops, I did want blue. So here we're going to have blank X blank and then another blank, and we moved because we moved right. And we're going to be in the state Q accept. And then the whole thing is finished because we're now in the state Q accept and we're totally okay. And so therefore we accept the input 0, 0. So 2 zeros is accepted by this machine because we ended in the state Q accept. If we ended in Q reject, then we would not accept the string. Okay, so what is this computing that we did? So each individual things right here along the way, so these are what are called configurations. Okay, so the configurations are going to keep track of several things. So the tape contents, the contents of the tape, the state that we are in, and the position that we are looking at on the tape. Formally, what it is a string W in the set gamma star, so the tape contents before, a single state written out as a string, and then gamma star again. That went off screen, so let me fix that. So formally, that's what it is. And the reason why you do it this way is that the two gamma stars are composing the tape contents, and the state, there's only one state here, and so therefore we have exactly one state. And the way you figure out the position is that the state itself is looking at the next position over here. So there's one character at least on this side of the state name, and that's the cell it looks at. I did it this way because you can easily see what it is, but if I wanted to write this formally, this one, for example, it would be blank X Q2 blank, because it's looking at the cell next to it. Okay, so then what is the whole thing that we're doing here? So this whole thing. So this thing is called a computation. So just similar to like how DFAs and PDAs actually work. So computation in the same way. So it's equal to a sequence of configurations. One more definition before I explain what a computation actually is. So each of these right here is something called a yield. So this configuration will yield this configuration. which means that you can apply a transition from one to get to the other one. Okay, so it's a sequence of configs, and I'm going to call them C0 up to, let's say, CM. So note that it's a finite list. So this thing says it's a finite sequence, such that C0 is the starting config. And how do I know what a start config is? Well, there's only one possible one, because you have to be in the start state, you have to be looking at the first cell, and the input string that's given to you after that. So it'd be Q0, then W after that. So that's the only possible starting config. And C sub I yields CI plus 1 for all I. Okay, so that defines a computation, just like we did before, because we're just applying a bunch of transitions right in order. Okay, so what other definitions do we need? Okay. So there are several other things that we're going to need here. So let's say that C is a computation of some kind. Then we'll say that C is accepting, and let's say that the configurations along the way are C0 through CM. We say that C is accepting if CM is CM contains the accept state, so Q accept. So like the example that we did above, where we had the 2 zeros ending in Q accept, is the same. That one would be an accepting computation, the whole sequence of configurations along the way. We will also say that C is rejecting if CM contains Q rejects, just like you would expect. One, believe it or not, is that C is halting if it is accepting or rejecting. So that informally, what that means is that the machine stopped, and in this case, I don't actually care whether or not it accepted or rejected. As long as it stopped at all, then we're good. And because it's deterministic, then that's good too. But halting just means it stopped. So then the language of the machine, of course, is all the strings in sigma star, such that M has an accepting computation on that string W. So the language of the machine is all the strings that it says accept on. It's unchanged, basically, from what we have known to be the language of a machine. No difference at all. So we say, so here's some important terms. So a language, let's call it L, is recognizable. I know there are other terms that are used for this, but I'm going to use recognizable if it is the language of some Turing machine. And I'm going to abbreviate Turing machine TM, of course. So, so it's recognizable if it is the language of some Turing machine somewhere. We actually do need another classification here, and we'll see why later, but the main reason is that if it has an accepting computation on the strings in the language, so the language is all the strings it accept on, if it says accept, it must stop. But if it doesn't accept the string, it could, in principle, run forever, because the computation is a finite sequence of configurations. If it takes infinitely many configurations on this string, then it's not a computation, and so therefore it can't accept those strings. So for the strings that are not in the language, it could theoretically run forever on those, so which is annoying. So the way that we get around this is we introduce a new classification of languages, which we call decidable. So a language L is decidable if it is the language of some Turing machine M, and M halts, which means stops, on all inputs. Okay, so no matter what input you're given, the machine eventually will stop at some point. Okay, so we say it's decidable if there's some machine with that language that it always stops on every string. It's recognizable if it stops and says except on the strings in the language. I don't care about the other strings that are not in the language. So as long as it halts and accepts on the strings in the language, then it's recognizable. But if we assert that the Turing machine also halts and rejects on the strings not in the language, then it's also then it's decidable because of that. So one thing that we can immediately notice from that little argument is that L being decidable implies that L is recognizable. Because recognizable is less strict on what it needs to be recognizable, whereas decidable has everything that recognizable needs and more. So if it's decidable, it automatically is recognizable. Okay, and the question, of course, is the converse true? So if it's recognizable, is it the case that it's decidable? And we'll answer that next time in the next live stream. Okay, so those are all the definitions that we need. So let's do some examples of what I call variants of Turing machines. So Turing machine variants. So variance just means that we can change the model somewhat, and we will get the exact same model back, equivalently the same model. So Turing machine variant. So one that I have come up with, so this is just purely my term, something I call a stay put Turing machine. So the tape head, oops, can't spell, tape head moves left, right, or S, and the S here means the tape head stays in the same cell. Okay, so the tape head stays exactly in the same cell, and it doesn't it doesn't move left or right. It's not forced to change either left or right one position. So clearly, and I'm going to abbreviate this with a STM here. So the S on the front means stay put. So a stay put Turing machine can simulate a normal Turing machine, because the stay put machine doesn't have to stay put on every transition. It can just move left and right and have no S on the transitions whatsoever. So a stay put Turing machine can simulate a normal one. But is the converse true? So can a normal Turing machine, I'll just write it, can a normal Turing machine simulate an STM? And the answer is actually yes. So let's see how to actually do that. So if the transition here, let's just say whatever it is, has an R or a left on it, so either left or right, either one of those two, then we can simulate this normally without any issue, because the normal machine can move left or right. So here we can just simulate the same transition without any issue. Okay, Am I getting a lot of drop frames? Because it's saying that I'm getting quite a few drop frames. That's pretty weird. Anyway, so, but I'll carry on anyway. So what if we have a transition, though, that has an S on it? So we can't simulate this normally because the normal model doesn't have an S on the transition. So what do we do here? What we're going to do is we're going to break this transition up into two transitions, where the first one is going to move right, because we can always move right. We don't necessarily can move left. We can always move right, though. And so the other transition is going to move left. So in effect, I'm going to skip over details here, but in effect, this transition right here is simulating the stay put transition, right? So it's kind of like the conversion between PDAs and CFGs, because we're simulating one thing with another thing. Or when we're converting from into Chomsky normal form for grammars, we're simulating one rule with other rules. Same idea here. You're simulating this transition with multiple transitions. Because at the end, once I get to this state, which is equivalent to this state, maybe I should give those names. So let's call this Q prime. So Q over here, Q prime over there, and this guy is Q double prime. Let's say it's a brand new state. And when I get to this state, I better be in the same state, same configuration that I was over here as I am here. So if I move right and move left, one thing we should note here is that these transitions don't, or at least that transition, don't change cell contents. Don't change the cell contents, because I don't want, because the transition before stayed in the same cell, then I don't want to modify the cell on the right of me. I only want to possibly modify the first cell, which we would do in this transition over here. Okay, so a normal Turing machine can simulate a stay put transition. And so these two models are equivalent to each other. Okay, let's do a few more. So x2. Something that I call a left reset Turing machine. So this thing can do left and right transitions. Let's just say only left and right transitions, although it won't actually matter for our purposes. But there's also a reset transition. And what it does is it moves the tape head immediately to the first cell in the tape, the leftmost cell. I should write that. So the leftmost cell. It moves it all the way immediately. Instead of one cell at a time, it's going to move it immediately over in one transition. So pretty clearly, just like before, actually I'm going to abbreviate this with LRTM, left reset Turing machine. So a left reset Turing machine can simulate a normal Turing machine, quote unquote normal Turing machine, because it doesn't have to do the reset transitions if it doesn't want to. But what about the other way? Can a normal Turing machine simulate a left reset one? So yeah, that's the question here. So can a normal Turing machine simulate an LRTM? And you won't be surprised to know that the answer here is also yes. And how do you actually do this? So the way that you do it is, so I'm just going to do it with a single picture here. actually with two pictures, I guess. So let's say that we have the input W1, W2 up to Wn here, and let's say that we have a blank here, blank, and then blanks after. So I'm going to draw a little vertical line here, and I'm going to continue it going down here, and you'll see why. So I'm going to convert this tape by moving it actually over one position. So I'm going to move all of the contents of the tape over one position, which means moving the input one position over. So it's going to look something like this. Hopefully that was on screen. Yeah. So we're going to have W1 over here, W2 up to Wn minus 1 on the left side of the vertical bar that I just made, and then Wn here, which indicates that I moved it over one position. Then blanks after that. But then you may be thinking, what is in that very first cell at the very beginning? And what's there is going to be a special symbol. So let's say a $. So this guy right here is a special symbol that's only going to be used for this purpose. It's only used for this purpose. So what we can do to simulate a reset transition, which is the only thing we need to do, what we do is we figure out, okay, where am I right now? And so I figure out where I am. Then I just do a bunch of left transitions over and 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 over until I hit this $. And because it's the only time it's ever used on the whole run of the machine, we can just keep going left. We'll never hit a $sign anywhere in here. And we're going to then hit that $sign. And so that will, in effect, do a left reset. And then to really get to the original first cell, which is this one, once I hit the $sign, I move over right one position. So pictorially, what that means is that if we had a transition that looked like this, so it was whatever we did, and then reset in the LRTM, so it had a reset transition. What we're going to do is, let's see, so let's call these Q and Q prime. So what I'm going to do is I'm going to, okay. So yeah, so what I'm going to do, let's just say, actually, let's just do it this way. So let's suppose that I am reading an X and changing it to a Y. Okay, so what I'm going to do then is I'm going to convert this into, here's Q over here. I'm still going to have X going to Y, but I'm going to move right, and because I'm not sure if I can move left. But what I am going to do is I'm going to have a state in the middle. I'm going to call Q double prime, and it's going to self loop on the following transition, which is going to be Z goes to left for all possible Z tape characters Z that are not the $sign. So if it's not the $sign, I'm just going to have a simple transition that will just skip over them going left. And then finally, what I'm going to do is, if I see that $sign at the beginning, I'm going to move right one position and go to the original end of the transition, which is Q prime. Okay, so again, I'm simulating this transition with this one. The only other weird thing you have to do is at the beginning, you have to shift the input right one position. And I'm not going to do that here, but it's actually pretty easy, and I invite you to actually think about how you would actually do that. But that's all that you would need to do. Shift it over one position with the $sign at the very beginning. And then after that, what you do is you just insert this between whenever you have a reset transition between two states in the left reset Turing machine. Okay, so then, of course, these two models are equivalent because I'm not interested in how fast the machine runs. I'm just focused on whether it actually computes the right thing at all at any point. Okay, so I'm going to take a quick break, and then we'll talk about two more interesting variants and get onto some more awesome stuff. So I will see you all in a bit. All right, so let's get back to fun things. So I want to talk about two more variants of Turing machines. So one thing that is kind of interesting is, why do we only have one tape? Why don't we have more? So we have a variant called a multi-tape Turing machine. So the way that this works is that we have some number of tapes we have to specify in advance. Let's say I have 3 here. So we're going to have, or maybe some in the middle, it doesn't matter. So I'm going to have K tapes right here. Let me use a different color for this. So I love notability, and I can change colors of anything I like. So nice. Of course it crashes. It crashes though. Plenty of times it crashes. And I gotta scroll down. That's annoying. So let's say that I have K tapes here. Okay. In this case, I only have 3. And we can have any types of things on the tapes. So I can have W0 through WN, then blanks after that. And then on the other tape, I might have blank R0, R1, up to RM, let's say, way over here. And then maybe I only have a single X on this tape, and then blanks immediately after. Okay, so I can have anything I want on these tapes. And the tape heads could theoretically be in completely different positions at each point. And also the fact that the tape heads could go in all different directions. So they don't have to all go in the same direction. So they're basically just independent tapes in some sense. Then what we will do then is the transition function will look at every single one of these observed values and then produce a sequence of moves and things to write. So the way to do this formally, so the transition function here is we're still going to have a single state, but we're going to look at K items on the tape, so K things on the tape, and what's the output of this transition? It's going to be a single state, just like before, K things to write on the tape, oops, and K left or rights. So by putting the K in the exponent, that just means pick K things out of this set and possibly duplicates. So this K here means pick K lefts and rights. They may all be lefts, all rights, or some combination of those two. Okay, so like this one I picked right, this one goes right, this one goes left. And it could be totally different depending on what is seen on any of the tapes. They're not truly independent, because if we have a different cell on this first tape, then it's affecting what's on the left side of this transition. And so it might be that the lefts and rights might be totally different if one cell changes up here. So it's pretty clear. You have to specify the number of tapes in advance. You can't just keep arbitrarily adding tapes as you go. But as long as you specify, oh, I want 3 tapes, then you're all good. So a multi-tape Turing machine with any number of tapes actually can simulate a normal Turing machine, and that's pretty easy to see, because what the multi-tape machine can do, even if it has more tapes, it can just only use one of the tapes. So use only one tape to do the work, and the other K minus one of them you can just move right. Move right and don't do anything. So that's pretty clear. What about the other direction though? So can a normal Turing machine simulate a multitape? And as you might expect, the answer here is also yes. And so what do you actually do here? So what you do is something that's kind of interesting. So what you do is we only have one tape to work with, but I'm going to make it look like, in some sense, that I do have multiple tapes at the same time. So the way that we're going to accomplish this is I'm going to have some special symbols, which are I'm going to call pound sign. These are going to be the delimiters between what we will consider to be tapes. So here is the tape 1 contents, and then a pound sign to be a delimiter, and then tape 2, then pound sign, and then keep going like this until we get to, let's say, tape K. And then pound sign, and then blanks after that. Okay, so we're trying to write down the contents of all K tapes. So that's the goal. So the goal here is to write down all K tapes contents on one tape. Now the issue with this, among many, is that we only have one tape head. So actually I'll write down all the problems that we can face here. So the problems that we have are that we only have one tape head. Right? So we only have one tape head, whereas in the multi-tape machine we're trying to simulate, we have K of them. So we got to figure out can we simulate all of this with one tape head? That's the first problem. 2, what if one of the tapes allocates a new cell? Right, because the tapes could theoretically move left or right, so any one of them can allocate a new cell. So if it's like, say, tape 2 here, and it needs a new cell right here, what do we actually do? So we got to figure out what to do there. The other problem, although that's less of a problem, is what if one of the tapes moves left off its left end? So what if like one of the tapes is at the very left-hand end and tries to move left? Well, what we can do is, once we do number 1, 2 and 3 come for free, essentially. So the way to get around this is we're going to increase. So the way we get around this is we increase the size of the tape alphabet. And you think, how is that possibly going to help? So the way that we're going to do this, and it's better to do it pictorially, is let's say we do something like this. So let's say we have the pound sign here, and then 0, 1, 2 maybe, and then 0, 0, and then 1, 1, 2, 3, and then it doesn't really matter what it is. So the way that we're going to do this is we're going to increase the tape alphabet size by having a copy of every single tape character other than the pound sign. So we're going to, so gamma prime is going to be gamma with a copy of okay, so let me write it this way. I'm just writing it formally. So it's gamma, just normal gamma, the things in the tape alphabet normally, but we're going to add in W dot, where W was an original tape character. And what this is, the process of, so this thing right here is a totally brand new character. So in a sense, we're doubling the size of the tape alphabet, because we take all the normal characters and then we add an additional copy where there's a little dot on top. So you may think, what is this dotting operation? It's just it's just a name for a new symbol. There's no such thing as a dotting operation. It's just a completely brand new symbol. It has nothing to do with the original one. But in the design of the machine, we're going to make this make it have different behavior. And also, of course, we're going to union in the pound sign because it's a brand new symbol for this machine specifically, and we shouldn't have a dot on it because the original machine didn't have pound signs because it's a brand new symbol. So the way that this is going to work is that the dot is going to correspond to where the tape head was on each of the original tapes. So let's just say it was like this. So in effect, what this means is that we had tape head 1 appear looking at that cell, tape head 2 looking at that cell, and tape head 3 looking at that cell. So the dots are recording for us where we should be on each of the original tapes. And to carry out a transition then, so to carry out a transition, what we need to do is to look at the K dotted cells. We need to figure out which K items to write into those cells. 3, we need to figure out which L or R we do in each tape. And 4, whether to allocate new cells. And 5, oh yeah, what was the 5th one? Oh yeah, to dot the corresponding cells. Okay, so like, for example, if say this cell right here, it was dotted before, if it said move right on this tape, this too should be dotted now. Okay, so then in the transitions we can say, if we see a 2 there and we want to dot it, we're going to write 2 dot into that cell. It's a totally brand new symbol, so it doesn't technically have anything to do with the 2, but we're forcing it to have some meaning to the 2 by writing it if there was a 2 there. Okay, so looking at the K dotted cells, that just, all that corresponds to is going from, so go from the beginning to the end in one pass. So that's pretty easy. And the K items to write, that will be embedded in the transition function. So this thing is embedded. God, I can't spell embedded. Embedded in the transition function delta. And same thing for what things to write on each of those tapes. And the way that we accomplish those is we make one pass over the entire input, or over the entire tape contents, I should say. Whether to allocate new cells, so that's kind of interesting. So the way to figure out whether this will happen is if we have something like, we have a Y in a cell that's dotted, we have a pound sign immediately after it and stuff. So what we need to do then is we're going to transform this into Y blank dot, because it moved right. It can only move right in that particular case. And then the pound sign with everything else after it. But the important thing is that this stuff over here is shifted right one position. And I invite you to figure out how to actually shift an input, okay? And because that's essentially what we're doing here. And then what you need to do is just come back here and write a blank dot symbol right there, and then that corresponds to allocating a new cell. And to dot the corresponding cells just involves one pass over the whole tape contents. And so that proves that essentially, I'm missing details here, but the basic idea in showing that if you have multiple tapes, you can simulate it with one tape. So you don't actually need multiple tapes, but the only purpose of them is to make the computation faster, because you don't have to zigzag all the way across the input, the tape contents. Cool. So I want to talk about one more, which, of course, the term you're all dreading right now, is a non-deterministic Turing machine. So the way that this is defined is, let's just assume that there's a single tape, because if there are multiple, then we can convert it to a single one and then worry about non-determinism. So here the transition function is going to be Q cross gamma, so the stuff on the left side is the same, except we can go to any number, hence the power set here, of Q, of what we had on the right side before. Okay, oops, need a bigger parentheses. So the right-hand side is the same, except we put a power set on there. So that means we can have any combination of really anything on the right side. Instead of exactly one transition to apply, I can have any number that I want to apply. Okay, and there's slight variations on what we can do here, but let's just keep it as is. And the way that we're going to accept a string, so we're going to accept W, a string W, if and only if there's some sequence of choices to get to Q accept. So, oops, we need to write the actual state name, Q accept. And this is very similar to how NFAs and PDAs actually work. So there's nothing strange going on here. But the only issue is that it might actually be the case that some computation paths don't halt, in the sense like they could just keep going on forever, because these machines can run forever. So we're going to say that a non-deterministic Turing machine, I'm going to abbreviate NTM here, is a decider if and only if all possible choices will eventually halt. It might take like a really long time, like way longer on some choices than other ones, but as long as every possible choice halts, we're all good. Okay, if it's a recognizer, then that's not really an issue. Oh, I actually didn't introduce that term, sorry for that. Decider just means it's the machine for the decidable language. If it's a recognizer, it's a machine for the recognizable language. Okay. So here is a decider if every possible choice halts at some point. So it's not like some choice will have the machine go on forever, and some will have it accept. Okay, so clearly, as we have already shown before, a non-deterministic Turing machine can simulate a normal Turing machine. Okay, a normal Turing machine, because it doesn't have to make non-deterministic choices. If it's not embedded in the transition function, then it would make non-deterministic choices. So the question is, can a normal Turing machine simulate a non-deterministic Turing machine? And as you might expect, the answer is in fact yes. So exactly the same answer as before. And we'll see kind of a reason for that in a little bit. So let's see. So what we're going to look at here is pretty famous, and you probably have heard of it if you've seen this before, but it's just nice to see again. It's something called a computation tree. Oh, Tyler asked, difference between a decidable language and a recognizable. So decidable means the machine has to halt, and recognizable means that it has to halt on the strings only in the language. So the strings that are not in the language, it's not required to do anything other than not accept. It either rejects outright or it can run forever. But the decider one has to halt and say the right answer. It can never ever run forever on any string at all. So so that's the difference between them. Okay, so what is a computation tree? Is we will have each of the nodes. So the nodes are configurations. So remember the start configuration and then applying transitions to get more configurations, etc. So in the normal machine model, it's just you start with the start config and you must have exactly one config come after it. You didn't have any choice. So it would just be a straight line down for a normal Turing machine. But a non-deterministic one can actually have multiple children. So the top one is the start configuration, but it could have a number of choices. So maybe this one on the left doesn't have any more choices. Maybe this one has 4, this one has 2, and then maybe this one has 3, and then maybe this one has 1, this one has 3. So it can keep going on like this. And of course, it could theoretically go on forever. But the interesting thing is that in general, these paths might not actually stop. So it might make this choice, and then this choice, and then this choice, and it just keeps going on down forever, possibly. So the way to figure out whether or not a machine, this machine actually could potentially stop, is if there is some random node in here somewhere which has the Q accept state in it. Because that's the only thing that we really care about. So if I do a depth first search of this tree, then I might make the wrong choice at the start because I'm trying to simulate this machine. I'm not running the machine. I'm trying to simulate it. So if I just say, oh, I'm going to make this choice and just see where it goes, then it might be that some choice will lead us down the garden path and we'll never actually hit an accept state, and we could theoretically run forever. So the way to get around this is to do a breadth first search of the computation tree. So how we do this, let me use blue for this. So we're going to look at the first level in the tree, and we see, does that have Q accept in it? And if it doesn't, then we're going to look at all of the children at level 2. Does any of them have Q accept in it? No. Then we'll look at the third level, and then we'll look at the fourth level, and just keep going down until we hit Q accept. And if we don't, we just keep going. So that's fine. So the algorithm here, so to speak, is do BFS one level at a time, and then if Q accept found, then accept. If no new nodes found, if we don't find anything new, then we will reject. And if it's neither one of those two, then it runs forever, but that's okay, because in that case, it must have been a recognizer to start with. So if it was a recognizer to start with, and there is a Q accept in there somewhere, then we will eventually find it because it's at some finite level. So at some point we will hit it. It just might take really, 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 really long. If there is no Q accept and it was a recognizer, then we won't hit this step possibly. So that means we could theoretically run forever, but that's okay because it's a recognizer, and that's totally okay for recognizers. If it was a decider before, if the non-deterministic machine was a decider, then that meant all computation paths halted at some point, which means that the tree is finite, which means that we will hit either one of these two steps, which means we will accept if we find it, and reject if we don't. Okay, and that's it. That will get us exactly what we will need, and we are in fact simulating the original one. How do you actually do the implementation of this? It's quite complicated, but it's actually not complicated. It just has a lot of details. So it's actually easy, but it has a lot of details. So the way that you do this is you will, for each of the children, you start with 0 and you label them with some number. So let's say I have 0 here, and then 1 here, then 2. Then for these children, I'm going to call it 0, 1, 2, 3. And then this one, 0, 1, 0, 1, 2, and 0. Yeah, so that one was 0. This one's going to be 0, 1, 2. So to figure out what thing to look at here, we just look at it and say, oh, I want to look at the configuration which is 1, 1, 2. So I follow the labels going down each of the transitions. And because I have them with different labels at each level, there's no possibility for there to be a duplicate somewhere. And so therefore, I just enumerate, I just list out all possible strings like this. There's actually an easier way to do it, which depends on the number of transitions coming out of a state. And then what you do is you just list out all possible strings that involve those characters. And then you just simulate for 0 steps, and then look at all the strings with 1 character, then all the strings with 2 characters, then all the ones with 3, and then just keep going. So that's effectively doing breadth first search. So it's exploring all the nodes at 1 distance away, then 2 distance, then 3 distance, then 4 distance, and then the same argument about whether or not you will hit the QAccept state will carry through exactly the same as before. Okay, cool. So you may be thinking, after all this, that Turing machines are the end of the line, because no matter what we think of, we can't find any model that's more powerful than Turing machines. And in some sense, that's actually true. And I want to give you a convincing argument of this. Here, if we have so can Turing machines do addition? If I can spell addition, that'd be good. Addition. So can Turing machines do addition? And the answer is actually yes. So in fact, all that we really need to do here is add by 1. So if we can add by 1, then if I want to add 2 whole numbers together, we'll see how to do that. But if we can add by 1, that'd be great. So let's say we have a binary number, 001, 011011 as an example. So if we try to add 1 to this, then what will happen is this 1 will change to a 0, then this one will change to a 0 because we're doing a carry, and this 0 will then be the end of the line, and it changes to a 1. So this will be 0, 1, 1, then the original 0 changed to a 1, and the last 2 1s changed to two zeros because they added by 1. So the algorithm here is start at the end, and move backwards. And then while the character is 1, change it to a 0, and then if the character becomes 0, change to a 1, and stop. And then if we hit the beginning, then we would have to allocate a new character. But I'm not really interested in the details here. I'm just focused on, can it in principle do it? And of course the answer is yes, because of this little algorithm right here. So we can move the tape head all the way to the very end, and then have a little self loop that just says, if you see a 1, change it to a 0 and move left. And then just keep going, and then have a transition that leaves that state on input 0, and then changes it to a 1 and maybe moves right or something. Okay, so it's easy to add 1 to a number. What if we wanted to do x plus y, so 2 numbers? So let's just say on the tape we have the number x and then delimited by a pound sign with a y after it. So I want to end up with something that is, let's just say, for example, x plus y on one side and whatever I want on the right side. So somewhere on the tape is written x plus y, the numerical value x plus y. So the way to do this is actually really simple. What we do is we add 1 to x, and then we subtract 1 from y at the same time. So I add 1 to x, and then I subtract 1 from y. And then I keep going, so keep going, while y is bigger than 0. Notifications. So as long as y is not 0, then I can just keep doing this add 1, subtract 1 behavior. I'm not changing the overall value of x plus y. So eventually what will happen is that I'll have 0 on this side, but that's okay. As long as I have x plus y written somewhere, then we got it. Cool. What if we wanted to do x times y? Well, that's just repeated addition. Right? We can do almost the exact same trick, and I invite you to actually think about how you actually would do this. But it's essentially just doing what we did before, but with adding a whole number instead of just adding 1. And we know how to add a whole number to something. What if I wanted to do x to the power y? Well, that's just repeated multiplication. And what if I wanted to do the max of x and y? It turns out that we could do something there too. That there is a way to actually compare the two numbers. So we can actually compare character for character against x and y. So compare them character for character, and we first have to check if one is longer than the other. Then we need to do things. But if at some point that one of them has a 1 where the other one has 0, then the one that has a 1 must be the larger one. Assuming that you start at the very end of the input, not at the very beginning, because we put the most significant bit at the beginning and not at the end. Okay, so there are actually some things that I'm skipping over that I normally would teach, but it's not really important for this. If you need to learn something called an enumerator, but that's I'm not going to actually do it here, but there's enough interest. But it doesn't provide anything that's totally new. If this is something that's new. So the thing that you can actually kind of at least get your head around is that if we have any mathematical operation on a computer, a modern computer, I mean, then a Turing machine can do it. I'm not saying that it can do it quickly or elegantly. I'm just saying it's possible in principle in a finite amount of time to do it. And that's pretty clear to see. It just might be horrendously slow, but it could it could potentially do it. So one thing that we will use pretty extensively, but at least implicitly, so not explicitly, is something called the Church-Turing Thesis. So this is not like a theorem that's not really provable, but it's something that is nonetheless true. Is that our quote-unquote intuitive notion of algorithms and Turing machines are equivalent because of the fact that we can transform any mathematical operation into something that a Turing machine can do. So if we have an algorithm that we wrote, it has a bunch of math stuff in it, we can transform it into a Turing machine. And so because of the fact that a Turing machine is now simulating our algorithm, we can also build a Turing machine simulator in our computers, and many people have done that. So Turing machines and algorithms really are equivalent to each other because I can always do a transformation from one to the other. It might not take the same amount of time, but, and we'll worry about that some other day, but the fact that they can do the same things in a finite amount of time, that's the key. The reason I can't prove this is we need to then write down what intuitive means. So this is not really provable as written here because we haven't defined what intuitive actually means. Like what operations are some weird, obscure operation that is more powerful than a Turing machine, possibly, than our computers, but we have never come across it, so we might as well just assume that this is a true statement. If you find such an operation, then please let me know. But for now, we're going to assume that they are equivalent to each other. So notably, if we can do something with an algorithm like we would normally write, then a Turing machine could, in principle, do it. And if there's something that a Turing machine can't do, which we'll learn about in the next live stream, then we can't write any algorithm to do it. Because if we could, then we can just convert it to the Turing machine that will compute the right thing. But in that case, there isn't one. Okay, so now what we're going to do is we're going to start talking about some problems for Turing machines. So the way that we're going to do this is we're going to talk about a high algorithm. And I'm actually going to skip over some details here that I would normally teach, but is not purely for the concept here. It's mainly to step away from the state machine diagram and to do something more general. So a high-level algorithm is just we're going to avoid all unnecessary details. Really is avoiding all details, but we're avoiding having to think about the very specific implementation of the Turing machine, but rather think about what is the Turing machine really doing. And a way to actually think of this is to write pseudocode. If you've done pseudocode, and I'm assuming you have if you're watching this stuff, if you write pseudocode, then that's perfectly fine. And that's essentially what this is. So avoiding, like, don't even worry about what the states are. Don't even worry about what the tape head is doing. Just don't think about it. Think about getting the problem and the algorithm across. But the problem is, if we want to answer questions about these machines, we actually need to be able to write them down into a string form. Because if we want to answer a question about whether, say, a DFA accepts an input, I need to be able to provide the DFA to the machine so that it can actually do the computation on the DFA itself. So we need to introduce something that seems totally off the wall, different than what we did before, but is nonetheless important, which is something called an encoding. So an encoding is taking a machine or grammar or anything, and what we're converting it into is a string that represents it. Okay, so I can just give you an example of how this would work. So let's say that we have a DFA here with states Q, sigma, alphabet, delta transition function, Q0 start state, and F final states. The way that we could write this down into a string is a character delimited string. So what I can do is, for example, I can write Q0, Q1, Q2, up to, let's say, QM, and then I can write S0 up to SK, maybe. And then the transition function, which is going to be triples. So I'm writing down the transition function now. So maybe Q0, comma A, comma Q3, and then maybe Q0B, Q6, and then we just keep carrying on with that. And then let's say that I write down all the transitions, and then I write down the start state. So maybe Q2 is the start state in this example, and then maybe Q0 is the only final state, just as an example. So here what I'm doing is I'm just listing out each of the things in a representative way in each of these 5 pieces. So all of these are the states in Q. So these are the states in the set of states. Here are the input characters. So and then here are the transition functions, or transition function, but all of the pieces involved in the transition function. This is the start state. And here's the set of final states. And once you know those 5 pieces, you completely know what the you completely know what the DFA is, because that's all you need to formally define the machine. Why is it that C language uses context? I'm not talking about context-free languages today. I'm talking about Turing machines and decidability. Okay, you can ask that question in a comment on that live stream. So the important thing to notice is that it doesn't matter which order that these are presented. If I tell you what order I'm going to write these down in, then you can extract all the pieces. So maybe like I write the transition function thing first, and then the final states, then the states, then the start state, and then the input characters. I could write it down in some weird ass way. But as long as I tell you what the way is in advance, then you can recover from it. You can figure out what the machine is going to do. So, yeah, so what we're going to do is we're going to agree on some encoding of the machine model in advance, but the details are irrelevant as long as, and this is the important piece, all relevant info, if I can spell relevant, that'd be good, relevant info can be extracted. So like in the DFA, if I get all of those 5 pieces, then we're all set. But if I can't do that, then it's not a good encoding. But we're going to assume that it's a good encoding. Okay, so what we're going to do is, let's say that we have a DFA or NFA or CFG or Turing machine or whatever. Let's call it M. So that's the thing that I want to encode. So M written out, I'll just put it here. So this thing is the actual object that we are interested in. So like a machine or a grammar or something. And then here's the really important part. If I put angle brackets m like this, so angle brackets with the machine, it actually could be multiple machines, but in this case we're going to start with one. So if it's one machine like this, then this thing is the string. So this is the string that is the encoding. Encoding of m. Okay. So however we encode it, that is the string that's encoding the whole machine. Okay. And so because it's a string now we can actually put it into a language, because we can't put a machine into a language. We can put a string into a language. Okay, so what we're going to do now is we're going to take a break and then talk about a ton of cool decidable problems. And I will see you all in a bit. Didn't have my mic on. Didn't have my mic on. Okay, so we're going to actually, let's see, how long's the live stream? We're actually going to finish quite early today, which is pretty cool. So I want to discuss a bunch of decidable problems. Decidable problems involving DFAs, CFGs, etc. So the first one we're going to talk about is something called A sub DFA. So, so what is this language? So the A here stands for the acceptance problem. Okay, and then the DFA downstairs obviously means DFA, but so what is this language? It's going to be the encoding. So remember, the angle brackets means encoding. So converting it to a string that's all that it means. It's mainly a formality, but we need to convert it to a string for this to make sense. So it's going to have two pieces, M and W, where M, no angle brackets. So M itself, the machine, is a DFA, and W is in the language of M, which in effect means that M accepts W. Okay. What you should also notice is that the W is carried along for the ride in the angle brackets here, and that's okay. So, like, one possible encoding is that we have £, and then however we encoded M in some way, it doesn't really matter. Then maybe after the last £, there, we put W1, W2 up to Wn, which is the string W, let's say. So we're going to carry W along for the ride in some context in relation to M. But again, because this is just encoding, as long as I can figure out where the W part is and where the M part is, then it doesn't really matter, as long as we agree to it in advance. But it's not really important what it is, as long as we agree to it. Okay, so what I claim to say here is that this language, the language itself, is decidable. This is what I claim. So that means that there is a Turing machine that has exactly this language. So it accepts exactly these strings and takes only a finite amount of time to do it. So how do we actually do this? So we're going to use something called a high-level description. I kind of alluded to this earlier, but I'm making it more explicit now. So how do you actually write a high-level description of something? What you do is you start with quotes, and then you say on input. It doesn't have to be exactly this, but as long as it's close, it's okay. So on input, MW, which is the same as this up here, so it has to match the problem that you're trying to solve. It has to match the problem you're trying to solve, which in this case is machine in W. So I put a qualification here where M is a DFA, and I can't say yet whether W is in the language of M because that's the problem I'm trying to solve. So all I can say here is that W is a string in sigma star, where sigma is the input alphabet of that DFA M. Okay, so then what we do is we write pseudocode. We just write step 1, step 2, step 3, and then maybe loops or whatever we need to do. So what we do is, how do we figure out whether a DFA accepts an input? Well, what we do is we just keep track of what state we are in as we are reading through the string W. So, so what we do is we repeatedly keep track of what state M is in after reading each character of W that's given. And then 2, maybe I should make this yellow too. I'll just redo it. So 1, that's the first step. So the second step is then we just figure out whether or not the state we ended up in is a final state. So if the last state was a final state of M, then the way to say that this machine that we're building, the high level description of, the way we say that it will accept is we say the word accept directly. We say accept. And then otherwise, if it did not end in a final state, then the way to say that this machine doesn't accept it is we reject outright. So we say the word reject. Okay, so reject means we immediately go to Q reject if we're trying to make the machine, but we're not interested in that. We're just focused on the high level algorithm here. In principle, you can convert this, assuming that you know how the encoding works. So it depends on the encoding, but assuming you can do that, then you can make the conversion over to the actual state diagram, which is good. So yeah. So the thing to note here is that we need to show that this thing really does run in a finite amount of time. Because if it doesn't, then I can't claim that it's a decider. So what we need to do is to show that each of these steps takes a finite amount of time. So I'm going to be really explicit in this example, but be less explicit later on because it'll be more obvious how it works. But what we need to do, say for this first one, is, well, we need to look at each character of W, which means we need to scan through the whole input, find the relevant character of W, which takes a finite amount of time. So that's no issue because the input length is finite in length. Then we need to actually write down what that state is that we're in, which means we got to scan to wherever the states are in the encoding, look up that state that we're currently in, and keep a record of that. Maybe write them down somewhere else, and then scan over to wherever the transition function's written, and then figure out what is the resulting state because of that. So we're in a certain state, and we have a certain input character, and then we just go through the transition function. We just find where that's listed, and then figure out where that third state is. So the state that we go to is the one that we're going to now say, now that is our current state. And we just keep doing this process over and over until we get through the whole input W. So each of those characters lookups takes a finite amount of time, and there are only a finite number of characters in W in total, because the whole input's finite, and W is a part of it. And so therefore, overall, there are only a finite number of steps taken for this first one. For the second one, all that we would need to do is it's actually a little less in this example, because all we need to do is to zoom over to wherever the final states are in the encoding, and then just check if the state we ended up in is one of those states. And we just linearly scan through them, and that takes a finite amount of time too. And so each of these steps in total takes a finite amount of time. So since this machine runs in a finite amount of time, it is a decider for this language A sub DFA. Okay, so we've produced a machine that will always halt on the strings, on every string, and has the right language, which is A sub DFA here. Cool. All right, let's do another one, maybe with less detail. So I'm going to call it A sub NFA, which is going to be almost identical, except M is an NFA this time, and W is in the language of M, just like before. So we can't do the simulation that we just did because there may be a bunch of choices that could be made. Maybe there are epsilon transitions, I don't know. So what we can do then is, well, because we've already done the work in solving A sub DFA, is there a connection between NFAs and DFAs? And of course there is. We can always convert an NFA to a DFA by the power set construction. So what we can do here is on input MW, where M is an NFA and W is in sigma star. What we're going to do is we're going to first convert this NFA M into an equivalent DFA. I'm going to call D. And then what we need to do then is just ask the decider machine for a DFA to answer the question about this DFA D and the original input W. Because the DFA D does exactly the same language as M, so the answer is going to be exactly the same. So what we're going to do then is we're going to run, the way that you write this is run the decider for A sub DFA on input, let's call it, it's D, so it has to be machine and input in that order. So the DFA is D itself, and the input we provide to it is W, because that's the input that went originally to M, and D is equivalent to M. It has the same language. And then what we're going to do here is we're going to output the same answer. So whatever the decider actually says, we're going to say the exact same thing. Okay, and this is good because we need to say accept or reject possibly if we want to make a decider. And since A sub DFA, the decider for it, runs in a finite amount of time, I can be confident that this step takes a finite amount of time. I'm just going to write finite to mean that. Well, what about this one right here? How do we convert M into an equivalent DFA D? Well, we just use the power set construction. And if M had n states, then D has at most 2 to the n states. And there was an algorithm to actually convert that. And it never ever took infinite amount of time. It always took a finite amount of time. So I can claim that this step runs in a finite amount of time too. And so therefore, since every step runs in a finite amount of time, and it has the right language because it had exactly the same answer here as the DFA one did, we can claim that this is also decidable. This language A sub NFA is decidable because we produced a decider, the machine, for it. So I can claim confidently here that A sub NFA is decidable. And actually, and hence is also recognizable too. Cool. So those are 2 quick problems. And I assume that you'll be able to tackle this one. I'm not going to actually go through it, but I'm going to call it A sub Rex. And what this is a Regex R and a string W, where R is a regex and W can be produced by the regex. And I assume that you can also show that this is decidable too, using the same technology, but I'm not going to do it here. Okay, so we're going to switch gears a little bit and talk about slightly different problem, which is what we're going to call the emptiness problem. So emptiness. Because it may seem completely weird that we're talking about this, but it turns out to be really important when we talk about Turing machines and related objects to them. So the emptiness problem is called E sub something. In this case, we're going to do DFA here. And here, it's going to be the encoding of a single machine, no input this time. So actually, I'm going to write that. So a no input here, no input W. So what we're going to have here is that M is a DFA, and the language of M is empty. Which, in other words, what it means is that the DFA doesn't accept anything at all. We're asking, what if we're given a DFA to us, can we figure out whether or not its language is empty? It doesn't accept anything. And this is actually pretty easy to do, but a lot of students miss this up. Because suppose we had something like this. So we have a DFA here, and let's say that we have something like this. It could be that its language is in fact empty, but it has a final state over here, let's say, or maybe let's say 3, like this. And there is no connection between from the start state over here, some way to get to this final state. So this is saying there could be a final state in the DFA, but it's just not reachable. So it's not enough to ask whether or not there's no final state in the DFA. You have to ask whether it's actually reachable. So one thing that we can do is do this. So on input M, so here remember it's matching the problem we're trying to solve. So a single machine M, where M is a DFA. The first step is to remove, so there are actually 2 ways of doing this, but I'm just going to do one of them, which is to remove all unreachable states from the start state Q0. So just remove any state you just cannot reach in any possible way from the start state. And the way that you can do that is look at this graph, look at the DFA as a graph. So remove all of the labelings on the edges and just do like something like breadth first search or something. And just take a note of all the states that you see and then remove any states that you never actually hit. So I'll just put a note here. You can run BFS once from Q0. So, and then if there's no connection over here to these states, you'll never get them anyway. If there is a final state that's still in the running, what you've shown that there is a way to get from the start state to that state. And so therefore there is a sequence of transitions you can apply to get to that state. Whereas if there is no way to get to any final state, then if you remove all those states, then there are no final states. So if there are any states, I'm going to call it F, in the set of final states now left, then we will accept, no, sorry, it's the exact opposite, reject. Why is it reject here? Because if there is a final state left, that means that the language of the machine is not empty, because there is a way for the machine to accept something. So here, we're trying to answer whether it is empty. But if there are any final states left, then that means it is not empty. So I should say, no, it is not empty by rejecting. And then, of course, otherwise, if there are no final states left, then you couldn't reach them to start with, and so therefore we will accept, which means because the language is in fact empty, because there were no states that it could reach in the first place. Okay, and I could phrase this problem for NFA, Rex for regular expressions, but it's exactly the same same setup that we had for the acceptance problem. You just make the conversions as necessary. There's no difference in terms of like emptiness there. You just make the relevant conversions. Okay. Why do I even talk about the emptiness problem? It's relevant later on, but it's also really important in this example, which is what we call the equivalence problem. So here I'm presented two objects of the same type. I want to figure out if they're the same. So this is, I'm going to call this EQ for equal, or equivalent, I guess. DFA, we can phrase this for NFAs if we wanted to, or regular expressions. So here we're going to be provided two machines instead of just one. So M1 and M2 are DFAs, and the language of M1 is equal to the language of M2. So in other words, these two DFAs, even if they look completely different from each other, they have the exact same language. Okay, so like if I'm trying to grade student submissions and I want to figure out whether the DFA is actually correct, even if it looks different, then I can just figure out maybe there's a decider for this, and if there is, then I can just plug my sample solution and their solution and see if the answer is actually yes. If it is yes, then they did produce the right answer, and if not, then I have some grading to do. But anyway, so this is the equivalence problem. And what I claim is that this thing is decidable. And there are actually three proofs that I'm aware of. So the first proof is, I'm going to shorthand this, is to minimize both machines. And check if the transitions are identically the same. Okay. So I'm not going to really prove this, but the main reason for this is that the minimal DFA for a language is unique. So if they did have the same language and I minimized both of them, then they should produce exactly the same machine. So if they're not identically the same, then they couldn't have been identically the same before. So, sorry, they couldn't have had the same language before, and so they weren't equivalent. Okay, so that's one proof. But there's one proof that uses the eDFA decider that we did before, and it's actually quite nice. So let's try to visualize what these two languages could be. So in general, these two languages are the language of the first machine and language of the second machine. They could be totally disjoint, like no strings in common, or they could be overlapping completely, like a circle. Or it could be that there's something like this where they're halfway in between. So what we want to notice is if they are equal to each other, what that means is that this shaded region right here, as well as this one right here, those two regions are empty if they are identically the same. So think about it. If you have a circle, if these two are overlapping so much that they're a circle, then these two regions are empty. And if they are not overlapping, then they are not empty. So what this means is that if they are equal to each other, then what we can say is that this region right here, so this region, actually I'm going to use different colors here. So this region right here is all the things that are in M1 and not in M2. So L of M2 complement. This thing over here is L of M2 and not in L of M1. So like this. So if I want both of them to be empty at the same time, then I want their union to be empty. Not intersection. It's empty. I mean union. It's union here because if one of the two is not empty, then I want to say no, it's not empty. So I only want them to be empty if and only if both of them are empty. So here what I'm going to do is I'm going to union these two sets together. And this thing is empty. So yeah, so this thing is empty if and only if L of M1 equals L of M2. So it's an equivalent way of formulating the problem. So why do I even do this? Why make it more complicated? Well, I can build a DFA for this. So I can build a DFA for this. And the reasoning is that regular languages are closed under complement, intersection, and union. Okay, so I can build a DFA for this entire left side just by doing a bunch of product constructions. There's actually another way to do it too, but let's just leave it like this. So I can build a DFA for this thing, and then the only other task I need to do is ask the eDFA decider if its language is equal to empty. Okay, so if this DFA, whatever it is, has empty language, then those the original two DFAs must have had equal language because you built a DFA for all the strings that exactly one of the two machines accepts and not the other one. So if there are no such strings, then they must have been equal to start with. Cool. So I'm not going to write out the high-level description of this because I essentially outlined it here. You build a DFA for this big boy. Then you just run the decider for eDFA on that gigantic DFA because all you need to provide is that single DFA and nothing else. And in fact, you can figure out whether two DFAs are the same. There is a third way to prove this, though, that it is decidable. In fact, I should clarify. Each of these steps along the way, this DFA is of finite size, so we can find it in a finite amount of time. And the eDFA already is a decider, so it runs in a finite amount of time. The machine runs in a finite amount of time. So the whole thing runs in a finite amount of time. So I want you to, so this is for the reader, I guess viewer? Got to think about that. For the viewer, there's a third way to prove this, is to use the pumping lemma. And if you can figure that out, what I invite you to think about is this language, inf DFA, which is going to be all the DFAs encoded in here, such that the language of M is infinite. And then I want you to show that this thing is also decidable in a very similar way. So it's actually pretty nice that you can use one proof technique to prove something else. So here, if you can actually show that EQ DFA is decidable using the pumping lemma, but you can also use the pumping lemma to show that inf DFA, this language, is in fact decidable. I'm getting notifications, lots of notifications. Okay, so those are quite a few problems involving DFA. You can ask exactly the same thing about NFAs, but you just, again, make the conversions to a DFA because they're equivalent. Then you can answer the same types of questions, like, is this DFA equivalent to this regular expression? And you can answer questions like that. I'm not focused on how fast it is. I'm focused on whether it can be done at all. At some point later, yeah, we could focus on how long it takes. But here we're only focused on whether it can be done at all. That's the main objective here. Okay. So hopefully not too, yeah, only a little bit more. So we only have 2 problems left to do. but they are kind of a doozy in some sense. So I want to talk about the acceptance problem, not for DFAs or something, but for context-free grammars. Okay, and I'm only going to focus on CFGs here, but you can focus on PDAs if you want to, and then just make the relevant conversions yet again. So the nice thing about all these problems is if you can answer it for one of the models, then you've already answered it for all of the equivalent versions of the same model. So like, once I did the thing for DFAs, I was able to do it for everything else, for NFAs and regular expressions immediately. So for CFGs, if I can answer this for CFGs, I've answered it for PDAs. So same thing for emptiness, same thing for equality, because I can always make the conversions in a finite amount of time, which is pretty cool. So I only have to do a little bit of work here. So here is, instead of a machine and a string, it's going to be a grammar and a string. So G is a CFG, and W is in the language of G. Okay, that was not the best L of G I've ever made. That's much better. Okay, so what do we actually do here? So the thing is that it's not like a DFA or an NFA where I could just convert it to the deterministic version of the same model, because I haven't done it on the live streams, but I've proven on the channel that recently that you can convert you can't convert any CFG into an equivalent deterministic version of the thing, because deterministic context-free languages and normal CFLs are different. They are different from each other. So I can't just convert it to a deterministic thing and then just run it purely off of that. I need to do something different here. So one thing that you can prove, and I invite you to actually prove this because you can do it pretty easily, is suppose that, suppose that G prime is a CFG in Chomsky normal form, and W is in sigma star. It's just a normal string with the length of W being n, and I require it to be at least 1 here, so it's not the empty string, but there's a way to fix that. Then any derivation of W in this grammar takes exactly 2n minus 1 rule applications. Okay, so this is a pretty famous result if you've in this class. I haven't proved it, but it's actually not that difficult to prove, because what you do is you try to figure out how many variables you're going to need to actually make in the first place, and the fact that because it's in CNF, you can only make one character for each of those variables at the very end. And so in total, you'll find that it has exactly 2n minus 1 rule applications. And in the case of where, here I should add, so if W is equal to the empty string, then it takes a 1 application. So the reason I didn't include this over here is that if n was 0, which is the length of the empty string, then 2 times 0 minus 1 is negative 1, which I don't think is possible to apply negative 1 rules. Okay, so therefore, if it's empty, then it would take 1 application, assuming that S goes to empty is a rule in the grammar to start with. But we'll deal with that as we go. So again, so I'll actually write it out this time. So on input, so G and W, so it has to match the language above, where G is a CFG and W is a string in sigma star. First step is to convert G into CNF I'm going to call it G prime, and the variables are going to be V prime, sigma. Sigma doesn't change because the language didn't change. The rules changed and the start variable changed, possibly. So then what we're going to do is, so if we're going to handle the W being empty condition first, and then otherwise we'll deal with the 2n minus 1 thing later. So if W is equal to the empty string, then we'll check, and S prime goes to empty is a rule in G prime. So if it is a rule, that means that the original grammar, because it's equivalent, was able to generate the empty string, and so therefore we should accept. Now I'm going to switch colors. If W is also empty and S prime to empty is not, I'm sounding like Borat there, not a rule in G prime, then we reject. Because the only way we could have made the empty string is if the start variable now makes it, because that's how CNF actually works. But if it's not there, then it didn't make it to start with, so we reject. But otherwise, what we do is we know it takes exactly 2n minus 1 rule applications, where n is the length of the string. So let's let n be the length of the string here. And then what we do is, I don't know which set of 2n minus 1 things to apply, so just try all of them. So try all possible 2n minus 1 rule applications. Oops. Yeah, if any of them result in W, in the string W that we're given, then we should accept, because that's the only possible way that W could have been accepted, is some set of rule applications actually made W. I never knew what they were in advance, so we're just trying all of them. And then otherwise, then we should reject, because the only way it could have ever been made is if it was made in exactly 2n minus 1 rule applications. But if we try all of them and none of them work, so it can't possibly be made. And it's pretty clear that this runs in a finite amount of time, because this conversion takes a finite amount of time and is completely algorithmic. These two are pretty obviously finite time, because we can just scan to see whether those rules are actually in there or not. This step clearly takes finite amount of time. I just add 1 for each of the characters in W and store that count somewhere. That's pretty easy. For this one, it's actually kind of difficult, but it can be done. The way you do it is you make a little counter that you figure out all the possible number of rules that could ever be made, and then in other words, you just make a list of size 2n minus 1, and you figure out which rule did you apply at each step. And then if you try one and it doesn't give W, you increment the last one. And once you exhaust all the possibilities for the last one, then you move up to the second to last one, and then you try all possible things that you could apply there. So there are ways to actually improve this, but it can be done in a finite amount of time just by trying all possibilities, and there's only a finite number of possibilities in this case. And clearly step 6 runs in a finite amount of time too. And so therefore, we can claim that a CFG is decidable. And hence, another word for therefore, a PDA is decidable. Okay. And because they're equivalent to each other, at the beginning for a PDA, I could just convert it to a CFG, which is an algorithmic process. And then I can just run the decider for a CFG. And then that's it. It's not fast, it's horrendously slow, but it can be done. Another method of proof that you can try here, and I'm not going to do here, is to use the CYK algorithm, which runs in polynomial time for grammars that are in CNF. Whereas this algorithm that I have here, the 2n minus 1 thing, is not polynomial time. But so if you look on my channel, I have done videos on the CYK algorithm, but I'm not going to cover them here. Okay, so one more to go, and then we will quit the stream. So it's the emptiness version. So we did the acceptance and the empty version. So here, just like before, we have a grammar. So G is a CFG. And the language of the grammar is empty. And I also want to claim that this big boy is decidable. Okay, so how do we actually do that? Well, let's think. So what does it mean to be not producing a string? So that means that there's no string in its language at all. Well, what would that actually mean? Well, what it would mean is that you can't ever get rid of a variable in the grammar. But it could be that, so this essentially means that the grammar derivations from the start variable, let's call it S, can never, quote unquote, get rid of a variable. Right? Because if it got rid of a variable, then it just produced a string, and we're asking if it, we're asking when it doesn't produce a string. So if it has an empty language, it can never get rid of the variable in the derivation. But it could, just like the DFA emptiness one, it could be that there is a variable somewhere that can produce a string only of terminals, like no variables at all. That's totally possible. In fact, I'll give you an example. So like if I have, say, S going to a B, where B produces just the character A and nothing else, and A produces little a, big A, like this. And of course, S is the start variable. Well, the variable B here clearly produces a string with no variables in it. But this grammar as a whole can't, because even though this piece of this rule can make a string only of terminals, this one can't, because the variable A can't. If I added or A to this, then it would, because A could produce a string that's full of terminals, but in the before case, it can't. So what we're going to do here is something like nullable, where a variable can produce the empty string, but here is something about being productive and actually being able to produce any string at all, not just the empty string. So we're going to say here a variable, let's call it X, is productive if X produces a string of terminals. So this thing right here is a string of terminals. And I'm going to change colors of that in a second because it looks like an eyesore seeing all this green. So let's say orange. Or it could be X going to, so the right-hand side of this rule is, let's say, x1, x2, up to xm, let's say. And why do I put these ellipses around? It could be that there could be terminals here. So the things in the ellipses are terminals. And what we require is that x1 through xm are all productive. So it's kind of like the nullable condition, which says that it's nullable if it can produce the empty string, and or it has a rule wherever it's just variables on the right side and all of them are nullable, because we want all of them to eventually produce the empty string. Here, what we're saying is that if x can be productive, which means make a string of terminals, if it directly does, like this, or it can have this rule where we extract all of the variables out. So all of the other stuff are terminals, which can be in any order, and all of the variables themselves are productive, which means they themselves produce a string. So x1 produces a string, x2 produces a string, etc., xm produces a string. So the entire thing could be a string in total. So for example, so for this one right here, B is productive because it obviously makes a string of terminals. A is not marked as productive, and S is not marked as productive. It could be marked productive later, but I haven't made it productive yet. And we've already tried all possible rules here, and so therefore, since S is not productive, it can't produce a string of terminals, even though other variables can. So the algorithm here is to repeatedly do the following. Repeatedly mark variables as productive if found. And then if no new variables are marked here, if they're not marked as productive, then reject. Sorry, not reject. Break out of this loop. And then out here, what we do is we check if the start variable S is productive. And so the answer actually is important here. So then it can be one of two ways. If yes, so if it is productive, which means it does produce a string, then we need to say reject, because we're trying to answer whether it is empty. If it is productive, then its language is not empty. So therefore I should say reject. And then obviously if no, then we should say accept. Because if it is not productive, which means it doesn't produce a string, therefore its language is empty, and then therefore it is, we accept there. So does this actually run in a finite amount of time? Well, obviously this part runs in a finite amount of time. That's pretty clear. Because it's just checking whether a variable is marked or not. For this one right here, it's a little less clear, because this loop actually can technically run forever, or at least it looks like it running forever. But the thing is, each one of these iterations, we're marking at least one variable as being productive, except for the very last iteration. Because at some point, because there are only a finite number of variables, I will either run out of variables to mark, or I will mark all of them. One of those two will occur, because there's only a finite number of variables. So it's at a finite point, we will break out of this. So each one of those steps, in addition, has to run in a finite amount of time. Each one of those times when we're marking variables. So how do we mark variables? We scan through all of the rules and then see whether we should mark it as productive. And that can easily be done because there are only a finite number of rules. So I can just scan through all the rules and then just mark them as productive as needed. Okay, so in fact, that's all that I really had. One thing that I want you to think about is say, EQ CFG decidable? Because we can't do the complement intersection idea because context-free languages are not closed under intersection or complement, so I can't use that idea. But that does not prove that this thing is undecidable outright, because there could be some other way that it can be shown to be decidable. But I want you to actually think about that before we do the live stream next time. But that's all that I wanted to do for you today. So that was the entire live stream on Turing machines and decidable languages. It was kind of shorter, but it sets the stage for all of the undecidable stuff that we're going to do next time. So hopefully that was interesting. Thank you for joining and supporting the channel. If you want to support the channel more, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description down below if you want to support the channel further. I accept donations via PayPal. If you want to donate, you don't have to. I'm doing one-on-one tutoring services if you want to engage in tutoring, maybe study for a final exam. If you want to schedule a tutoring session, then email me at the email down below. I will always be grateful for all of your support and help you as much as possible. So thank you all again for watching the live stream. And as always, I'll see you.